slides. This is the fourth if you are going in order. And here we're going to talk about how solar energy is functionally distributed at a number of different scales. So geographers are really concerned with scale. How big or how small is something? And oftentimes we will talk about a global scale, a regional scale, a local scale, and a micro scale. And globally, locally and regionally is how a lot of solar energy is rotated through. We can also think sort of micro as well, but functionally for this class, micro is sort of irrelevant. So the big distribution mechanisms for solar energy is conduction, convection, and advection. And I'm going to repeat these on the next slide because the diagram there works really well. So conduction is the transfer of energy from one molecule to another. So if we were to use our pool balls again, our cue ball and the 8-ball, for instance, as that cue ball strikes the 8-ball, it's going to then transfer some of its energy to that cue ball, and it's going to initiate movement in that cue ball or in the 8-ball. And that 8-ball may hit another ball which is on the billiards table, and it may then transfer what energy it has to that then ball, the striped 7, for instance, and then it's going to initiate some transfer of energy and move, and it may strike another. And consequently, what you're going to see is there's going to be less and less energy available to transfer to the next object, because the energy is being used up in movement. So this is the law of conservation of energy. So we've got this happening. So with conduction, as solar energy comes in and strikes a molecule, it's going to set that molecule up to vibrate. And the faster it vibrates and the more it vibrates, the more space it's going to take up. And it's going to then have a greater opportunity to interact and strike another molecule, which is in vicinity. And if it strikes that molecule, it's going to then transfer that energy, and that molecule is going to vibrate and move and shake. And as it's vibrating, moving, and shaking, it's going to strike another. So we know when the atmosphere is cold, the molecules are close together. And so if solar energy comes in and strikes just one, because all those molecules are close together, that one is able to hit everybody that it's close to. Imagine standing in a really crowded room where nobody can move. You can reach out and tap a whole bunch of people on the shoulder without too much effort, right? You don't have to expend a lot of energy. And as you tap everyone on the shoulder, they're going to whip their head around and they're going to, you've excited them. Like, who's touching me? What does that person want, right? So you've initiated a lot of movement just by being the person in the center. That's engaging, right? So this is what will happen in the atmosphere as well, is one molecule is now engaged with some solar energy, and it can transfer that energy and get the others to move. Think of that old telephone game that we used to play when we were kids, and we sat in a circle, and the first person would whisper into the ear of another individual and say, "Hey, I like to eat macaroni and cheese." And then the next person whispers, Dave likes to eat macaroni and cheese. And by the end, it's like Dave likes to run around the circle with his dog, because somebody got it wrong. The transmission was diminished the further away you got from the source. On this diagram, conduction is what's happening here in the handle and the hand of this pot. So the energy source, the sun in this would be akin to the heating coils on the stove. It's transmitting to the pot. The pot then, molecule by molecule, is moving energy up the sides of this pot into the water within this pot, and then across to the handle. And you're going to feel the heat of that handle. It's not going to be as intense, thank goodness, as the heating coils, but you're going to get some volume of heat. Now, depending on what that pot is made out of, the transmission rates can be better or worse. If it's not a great transmitter, then that handle's going to feel rather cool. If it's a great transmitter, sorry for my stuttering, if it's a great transmitter, then that handle's going to feel rather hot and you might get a burn. All right, so atmosphere works the same way. Conduction is what's happening with the fluid in the pot. Now, conduction's happening here with the pot because the pot is rigid and we don't have a lot of liberation to move that pot. But don't forget that every little molecule is functionally moving in that metal. All right, it's not completely static. So convection then, the surface feature, this radiant energy coming out of these heating coils, is heating up the bottom of that pot. And as it heats up the bottom of the pot, the energy is going to be quite significant. The molecules are going to move more. As they move more, they're going to take up more space. As they take up more space, they become more buoyant. Because they're more buoyant and because they also have a lot of energy in that buoyant mass, it's going to lift because it's going to be less dense than the water in this case around them. The atmosphere is a fluid. It works the same way. You're going to energize the molecules of the atmosphere. They're going to move rapidly and take up more space. And as they take up more space, they're going to be more buoyant and they're going to lift. You've energized and you've created volume in the atmosphere and you've created lift. So I want to say a couple of things with that. One example that works really well for the folks that are cookers out there, they like to cook. When you crack an egg in a bowl, the egg is pretty dense and it's sitting at the bottom of the bowl. But you start to whisk the egg. What you're doing is you're adding energy to that egg. And you whisk it enough and it becomes fluffy and frothy, right? You've added volume to that egg and that egg has expanded and it's lifted through that bowl. It's taking up more space. So it's the same concept here. We're lifting, we're adding energy to something, so there's a volumetric increase. But the egg is light and fluffy and the water is kind of light and fluffy, but the air is also light and fluffy as well, and it's going to rise and it's going to continue to rise as long as it's more light, buoyant than the surrounding air around it. All right, so that's convection. Your stove, for the most part, most stoves, convection stoves work the same way. The heat is on the bottom. That air is going to rise up in your oven. And as it rises, it's going to hit the top of your oven chamber, and then it's got nowhere to go. So it's going to move across the top of the oven to the corners of your oven where you're furthest away from the heating coils. Now, because you're far away from the heating coils, you're losing energy. And when you lose energy, you become dense. The molecules come close together and it falls back to the surface of the oven, where it's going to then heat up again, and as it heats up, it rotates and then lifts. So you get this rotational effect that is exemplified in the diagram right here. So it's warm, warm, warm. We're far away from the heating coil here, so we're going to cool off and drop back here. So you get this churning effect. Same thing happens in the atmosphere, right? So this is convection. So the heat that's here gets transferred upwards into the cooler parts of this pot, likewise to the cooler parts of the atmosphere. And if this rotation has volume in distance this way, we're going to move it laterally as well. That lateral movement is important on the bottom because that is advection. That's this right here. We've now got some volume of charged energy coming down. It's reaching the bottom of the pot or the bottom of your stove or the bottom of the atmosphere, which is the surface of the earth proper. And it's going to hit the surface of the earth and it's going to then move across the bottom of the pot or across your stove or across the surface of the earth. Advection is a fancy word for wind. All right, so this is how we're generating wind. We're going to move from the cool area to the warm area. Where things are cool, they're dense, it's high density. Where it's warm, it's low density. So I will repeat this a few times, but wind is the movement from a high dense environment to a low dense environment. Think of if you're sitting and you're taking a horrible test and you just like, I hate this test. There's nothing more than you want to do is to get up and leave. And the worse the test is, the faster you want to leave. You're under a lot of pressure, right? And when people are under pressure, you're into flight or fight, and both of them involve movement. And so the conditions that work for humans and other animals are the physics that move through earth processes as well. We always move from high stressful environments or high intense environments to low intense environments, and wind is the same thing. So with this second slide from this set is then this solar energy. All right, so solar energy, as we know, is mostly going to come in between 23.5 degrees north and 23.5 degrees south latitude. Nice heating here daily. At the global scale, we're going to break this up, and I'm going to make you all unhappy with the next module. So you are formally warned that you might want to spend a little extra time with the next module. We're going to warm up the surface of the earth here, just like we're warming up the surface of the oven. So heat starts at the surface of the earth. That air parcel is going to rise, it's going to come up, it's going to hit the top of the troposphere. Remember, that's the tropopause, where it's the coolest. It can't, like on a lid of a pot, it can't continue out here, so it's going to hit the top and it's going to have nowhere to go except towards the pole here and towards the pole here. We're far away from the heat source. Here's our heat source right here. We're far away from the heat source here, so that energy, you can see it's dropping, it's getting more and more dense and falling. Dense and heavy, falls here and then rotates back towards the equatorial region. All right, notice that I did not say the equator, I said the equatorial region. All right, so this big band right in here. So we have, if the earth did not rotate, we would have two big winds, one that comes from the Arctic to the equator and one that comes from the Antarctic to the equator. And so you never have to ask what direction is the wind blowing from. It's always going to blow from a pole to the equator. And so that's the general atmospheric circulation of our planet. That's these big convective cells. But the Coriolis effect splits those cells. And again, I'm just starting this conversation here. We're going to get much deeper into it a little bit later on. But the Coriolis effect splits this, so we've got lifting that takes place in the equatorial area as well. We're going to come up, but then because of the Coriolis, things start to fall at around 30 degrees latitude, both in the northern hemisphere and the southern hemisphere, okay, folks? So where this yellow zone is where we're going to get air falling, but it's not really cool air yet, right? Look at where we're at. We're at northern Mexico, southern California, southern Arizona, across to Florida. Not a cold location, right? So we're going to get falling air here. Some of that air is going to come across and become a wind that's going to come back to the equator, and some of that's going to come and be a wind that's going to move towards around 60 degrees north, and then it's going to lift. Now, little diagram here, we show a cloud mass generating here, and we've got a cloud mass generating here. Notice no cloud mass here. All right, so we're going to lift and we're going to create this convection cell of lifting and falling. And then we've got to have a third one here, lifting and then falling back at the poles. All right, so this is how solar energy atmospherically is transferred through to higher latitudes where there's less solar energy every day of the year because of those high latitudes. All right, gets a little bit more complex because we get some lateral movement, but there is a great start for you. All right, guys, I'll be on to the next set of slides here immediately.